Well, the first test that we will use to determine the convergence or the divergence of a series is the nth term test. And I would even add that this is probably the easiest test that we can use. And what this test tells us is that if we have an infinite series of sum a sub n, then this series will diverge. So this series diverges if the limit as n approaches infinity, the limit as n approaches infinity of a sub n does not equal 0. So if it equals any other number, even positive or negative infinity, then this series will diverge. Also, if, or I would even add, or the limit as n approaches infinity of a sub n does not exist. So does not exist. For example, if we had some limit that just oscillated forever between -1 and 1 or other values, and it never converged to a specific value, then this series will also diverge. Now, it's important to realize that if the limit as n approaches infinity of a sub n does equal 0, if it does equal 0, well, this does not imply that the series converges. So we know that the test is inconclusive. So we cannot use the nth term test to determine that a series converges. We can, however, use this test to determine that a series diverges. In the case that the limit equals 0, then it's inconclusive, and we need to move on to another test. So it's not really that helpful for determining whether a series is convergent. However, it is a very easy and quick test to apply to be able to determine whether a series diverges. And that way you don't need to spend your time doing other tests like the integral test or the ratio test or any other one to determine convergence. So let's look at a couple of examples so we can understand this better. So the first example, we will have the sum from n equals 1 to infinity of n cubed. And the question is, does this series diverge? Well, if we apply the limit, if we say, okay, well, the limit as n approaches infinity of, well, what is our a sub n? Well, our a sub n will be whatever is right there in front of the sigma. So we have the limit as n approaches infinity of n cubed. Well, as n gets progressively large, and as it tends toward infinity, well, n cubed will obviously grow without bound, right? n cubed looks something like this for values of n is greater than 0. So it will grow without bound as n goes towards infinity. So the limit as n approaches infinity of n cubed is equal to infinity. And since this does not equal 0, since the limit does not equal 0, then it diverges by the nth term test. So diverges. Okay, that was fairly straightforward. Let's move on to the next one. Well, in the next example, we have the sum from n equals 1 to infinity of 2n squared over 3n cubed plus 1. And we can apply now the nth term test. So we say the limit as n approaches infinity of 2n squared over 3n cubed plus 1. And we could, if we evaluated this directly, then we would see that we would have an indeterminate form. We would have infinity over infinity. But we could apply L'Hopital's rule a couple of times, or we can realize that the exponent, the highest powered exponent in the numerator is 2, and the highest powered exponent in the denominator is 3. And since the highest powered exponent in the denominator is higher than that of the highest power exponent in the numerator, that this would converge to 0. And since this converges to 0, meaning the limit as n approaches infinity of this equals 0, it means that we cannot determine divergence from the nth term test. So the nth term test, nth term test would yield an inconclusive result. So inconclusive. Now, this doesn't mean that it doesn't diverge. It doesn't mean that it does converge. It just means that we have to apply another test. We need more information to be able to determine how this series operates. Okay, now for our next example, it'll be very similar to the last one. Instead of having a power to a squared power in the numerator, we will have a cubed power. So now we will have 2n cubed over 3n cubed plus 1. And you can see that these are very similar. All we've done is we've raised the power of the n squared to an n cubed in the numerator. Now if we apply the nth term test, we will take the limit as n approaches infinity of 2n cubed over 3n cubed plus 1. Now, since we have the same highest powered exponent in the denominator and the numerator, we have an n cubed, well, we know that the limit as n approaches infinity of this will just be equal to the ratio of the coefficients of the highest powered exponent. And that will equal, well, we have a 2 in the numerator and we have a 3 in the denominator, so that will equal 2/3. And since this limit does not equal 0, since it does not equal 0, in other words, it equals 2/3, then by the nth term test, so by the nth term test, this series diverges. Okay, so on to another example. In example 4, we have the sum from n equals 1 to infinity of e to the n over n squared. And once again, we will take the limit as n approaches infinity of e to the n over n squared. And as we take this limit, what we will realize is we will say, okay, well, we know that the function e to the n grows faster than n to, and I will actually write this a different way, a way that you'll probably see it a lot more often, and then I will replace the x's, the n's later on. So e to the x, right, the function e to the x grows faster than x to the n, meaning if we have any function x to the 10th power or even x to the 100th power, well, e to the x will always grow faster than any x to any power. So when we take the limit here, now we're going to replace our x's with n's, and in this case our exponent is 2 in the denominator. Well, we have e to the n over n to some power, and we know that e to the n will grow faster than n squared, so that means that this limit will equal infinity. Another way that we could have done this is by applying L'Hopital's rule. We would have been able to determine that. Okay, so since this limit equals infinity, then that would imply that this series diverges. Once again, by the nth term test, since the limit does not equal 0, since it equals something other than 0, then we know that it diverges. And for our last example, So question 5, we have the infinite sum from n equals 1 to infinity of -1 to the n plus 1 times 1 over n. So we know that this is an alternating series. We have this oscillator, is what I like to call this, because it makes our function oscillate. So we have this oscillator multiplied by 1 over n, and we want to determine whether this diverges or not. So what we will do is we will apply the limit. We will say, what is the limit as n approaches infinity of -1 to the n plus 1 times 1 over n? Well, as this first part, as this oscillating part goes to infinity, what we will have is we will basically have -1 and then 1 and -1 and then 1, on and on and on. So that's not necessarily going to converge to any one value. However, when we take the limit of this second part, so of this 1 over n, as n approaches infinity, that will equal 0. So what we will have is we will have numbers that are getting progressively smaller, and they'll be flipping between positives and negatives and positives and negatives. But they will become so small that the sign won't even matter, and this limit will equal 0. And since the limit equals 0, the nth term test is inconclusive. Inconclusive, which means that we cannot determine any results about this series with the nth term test. Well, I hope you found this video helpful. Please, if you have any questions, leave a comment below. I'll be sure to respond to them, and I will see you in the next video.